Polynomials are the core engine of algebra. If you ask a mathematician what algebra is, an acceptable answer would be that algebra is really just the study of polynomials. And it really is. It really is. Think about what you've learned so far in algebra. Linear equations and quadratics are 90% of what Algebra 1 is about. Polynomials are the name given for constant linear and quadratic expressions. But they also introduce cubics, quartics, and quintics. The exponent, also known as the degree, can be any counting number. The coefficients can be, in contrast, any number imaginable. It is only once you decide to turn the exponents into something unnatural that you no longer have a polynomial. Another restriction on a polynomials is that you can't have an expression like the absolute value of x or sine of x and call it a polynomial. The face of a polynomial is that they are expressed as a sum of terms that are an unknown raised to a natural power and multiplied by any coefficient. This should be easy to remember though. 90% of what you learn in algebra so far are polynomials. In this chapter, we will take an analysis of polynomials, which include cubics, quartics, and quintics, by applying operations, factoring, and analyzing their curves that they depict. A polynomial in its factor form is still considered a polynomial. This is because they can be expressed as a polynomial. Yes, a polynomial that is not a polynomial is a polynomial because it can be expressed as a polynomial. Of course, this doesn't just apply to factoring. Any, quote, unsimplified polynomial is a polynomial. But it is better this way because the factor form of the polynomial still has the same properties which the expanded form has. The x-intercepts are the same and so are the y-intercepts. But why polynomials? Why should we have a specific classifications? Why do we need to learn about them? 3 things. 1. They are common in real life. Many real-life situations can be modeled as a polynomial. 2. The knowledge of polynomials is essential in continuing your journey in math. One cannot craft a wooden sword without sticks, which cannot be crafted without wood, which cannot be crafted without punching a tree. And the third reason is what makes polynomials as interesting as they are. Polynomials are the simplest way to express a specific curve for a given domain. And why is that important? The answer is that polynomials are simple. We have formulas to find solutions for quadratics and even cubics or quartics. And although there is no formula for quintics and polynomials of a greater degree, we can always approximate the solutions with computers. The computers can follow a very specific algorithm that is easy to apply just because they are polynomials. I hope you now understand the importance of understanding these expressions because that's what we're going to do from now on. First, operations on polynomials. Adding and subtracting are what we should be able to do while sleeping. Combine the like terms, remembering to distribute the minus sign if there is one. Multiplying and dividing may be tricky. When we multiply factors, we utilize the distributive property. For instance, in this equation, I first distribute the first term of the first factor in the first, second, and third terms in the second factor. We then repeat the process for the second term. A way to visualize this is to draw out a square and divide it into a grid. Then the length and width of the square are the sums of each term in the factor. And we know what the area of each square would be. It would just be the product of the respective column times the respective row. Each piece contributes to the whole area, which is the same thing as finding the product of a polynomial. Essentially, expanding factors is finding all the combinations possible for each pair of terms. But the most efficient way to do that is to use this rainbow technique. Remember that, because this will be key to understanding Pascal's triangle, which is coming up after this exercise. But what if we have the same expression a certain number of times? We can do the same thing we just did, but as all things with symmetry, there is an elegant pattern. there's going to be an a cubed and b cubed somewhere in the expanded form. There will also be an a squared b and an ab squared term in there. But how will I know the coefficient of a squared b and ab squared? The key insight here is that the coefficient is just the total number of times when the variable with a certain power can be formed. For example, the expanded form of a plus b times a plus b is a squared plus ab plus ba plus b squared. In this case, the coefficient for ab is 2 because there is a total of 2 combinations, like I mentioned earlier, where you choose an a and a b. Now, because the expanded form is just every combination possible, another way to write this is to write every a plus b into an a or b. Each time we make a coefficient, we have an option to choose which variable we want from the factor. But the chosen variables can't be chosen in the same order twice. So, how can I find the coefficient for the a squared b term? For that, it would just be the number of ways I can choose 2 a's and 1 b from this expanded expression. There are 3 ways to do that: BAA, ABA, and AAB. As for the coefficient of AB squared, that is the number of times we can choose 1A and 2 B's, which leads to the same number of combinations. So the answer is A cubed plus 3A squared B plus 3AB squared plus B cubed. This formula is actually just saying that there is 1 way to arrange 3 A's, 3 ways to arrange 2 A's and 1 B, and so forth. Here's where it gets interesting. How would I find the expanded form of a plus b to the 4th? I can do the same thing I did before, where we count the number of combinations possible for a certain number of a's and b's. But I'm not going to do that. I'm going to use a trick. I can split it into 2 individual cases. For example, a method of counting the number of squares that are green or red is to split it into 2 cases. The case that the squares are green or the case that the squares are red. Now we can simply add the 2 cases and obtain the same result as if we counted the squares that are green or red. Another trick we will use is that we can ignore a variable. What I mean by that is that instead of considering the number of ways we can choose, let's say 3 a's and 1 b, we will get the same number of combinations if we simply consider the number of ways that we can choose 3 a's from a total of 4 options. The number of variables we choose will always be 3, and the number of variables we don't choose will always be 1. What's happening here is that in one of the 4 options, I'm simply not taking a variable. So let's begin. We know that the outer terms are going to have coefficients of 1, and we know that we will have an a cubed b term, an a squared b squared term, and an ab cubed term. Let's first start by finding the coefficients of a squared b squared. This is the same thing as finding the number of ways I can choose 2 a's and 2 b's from the 4 options, which is the same thing as finding the number of ways we can choose 2 a's from 4 options. Now, before I proceed any further in finding the unknown, I notice that this expression is a little inconvenient. The expression a times question mark times question mark doesn't exactly signify anything other than selecting 2 a's from 4 options. And that's not exactly what I want. I want to find the number of combinations possible of selecting 2 a's from 4 options. That's why we are going to introduce apt notation. I'm going to write 2 from 4 to signify that I want to find the number of ways to choose 2 variables from 4 options. Now I can find what my 2 cases are going to be. Ideally, I want my case to be some number that I already know. Earlier, we discovered that there are 3 ways to choose 2 a's from 3 options and 1 a from 3 options. That will be written as 1 from 3 equals 3 and 2 from 3 equals 3 in our new notation. Wouldn't it be so convenient if I could just add these 2 numbers together as individual cases? I want to find 2 from 4. How can I reframe 2 from 4 so I can use these 2 convenient numbers I found already? Here, I would check what is different between what I want and what I already know. I want to change 2 from 4 into 1 from 3 and 2 from 3. So maybe I would think of setting one variable aside. That would get me what I want, right? But now I've lost the 4 option, meaning that at the moment we don't know if 2 from 4 is equal to the 2 cases yet. That's not going to work. For that reason, it's possible that I might think of setting an A into a special A, meaning that every time I choose to pick 2 from 4, I either have that special variable or not. This way, I have 2 cases, and those 2 cases will add up to 2 from 4, because if I ignore the fact that I have a special A, I end up wanting to find 2 from 4. In fact, those 2 cases are 1 from 3 and 2 from 3. 1 from 3 would be the same thing as the case where I have the special variable. Since I already know that I already have the special variable, in this case, I no longer have to choose 2. I only have to choose 1. Likewise, I only have 3 options because I already know that I have the special A. 2 from 3 is the same thing as the number of ways to not choose a special A, because I still have to choose 2 normal A's in this case, but I know that I don't choose the special variable, so I have 3 options. Therefore, our coefficient is the sum of these 2 cases, which we already know to be 3 and 3. Now this is what I like to call an epic math gamer moment. It's what makes Pascal's triangle a triangle. It generalizes to the formula where choosing k from n is equivalent to choosing k minus 1 from n minus 1 plus k from n minus 1. It tells us that if I set a special variable, then I can split k from n into 2 cases, k minus 1 from n minus 1 and k from n minus 1. K minus 1 from n minus 1 is a case where I do choose a special variable, and k from n minus 1 is where I do not choose a special variable. And one final little detail. I use the notation k from n to signify that I want to choose k from n, but conventionally in math, we write it in the following form, which is read as n choose k. Meaning that I have n things, but I want to find the number of ways I can choose k things. So, literally, n choose k. Our identity then translates to n choose k equals n minus 1 choose k minus 1 plus n minus 1 choose k. This funky expression is actually another operation, just like addition and multiplication that we just discovered. Go to Google, type a number, type choose and type another number. This number that Google spits out is exactly how many ways one could find combinations for k things from n options. If you understood that, which if you didn't you should rewatch, you now understand Pascal's triangle. Pascal's triangle is the triangle that I can form once I realize that I can use the formula to find an infinite number of n choose k. I start the triangle by putting in what I already know. Anything choose 0 is 1. There is one way to choose anything from 0, which is to choose nothing. Also, anything choose the same number is 1 because there is one way to pick everything from everything. Now we fill in the blank with our formula. By our formula, the numbers we don't know are conveniently the sum of the top left and top right numbers of the number we want to find. 2 choose 1 by our identity is 1 choose 0 plus 1 choose 1 equals 2. 3 choose 1 is 2 choose 0 plus 2 choose 1 equals 3. 3 choose 2 is 2 choose 1 plus 2 choose 2 equals 3, and so forth. We continue this by just finding the sum of the two numbers on the top left and right. So when you write Pascal's triangle, first you write 0, 1, 2 to denote the number of things that you want to choose from. Then you write a 1 and decode each row below by the sum of the 2 or 1 numbers on top. Now we can use Pascal's triangle to solve our original problem. All we need is the coefficient for a cubed b and ab cubed. The coefficient for a cubed b is 4 choose 3, and the coefficient for ab cubed is 4 choose 1. By the way, notice that we can also claim that the coefficient for a cubed b is 4 choose 1 if we use the reasoning that we want to find the number of ways we can choose 1b from 4 options instead of 3a's from 4 options. As we can see from Pascal's triangle, both lead to the same number. That makes sense. Either way, the coefficients are 4 and 4 because those are what the corresponding numbers in Pascal's triangle are. And we are done. In this example, first we expand like we are familiar with. Now we reference Pascal's triangle. 5 choose 5 is 1, 5 choose 4 is 5, 5 choose 3 is 10, 5 choose 2 is 10, 5 choose 1 is 5, and 5 choose 0 is 1. Then simplify to obtain the result. Division with polynomials is very similar to the long division we learned in elementary school. First, I write out the traditional notation for long division. Then I find a term that will perfectly match with our leading term when multiplied with the divisor. That would be x squared. X squared times x plus 1 is x cubed plus x squared, which will cancel out the cubed term for us. So subtract that from the dividend, which yields x plus 3. The next term as the quotient would be 1. 1 times x plus 1 perfectly matches with the x. The leading term of the product is x, meaning that it will cancel out the linear term for us. So evaluate 1 times x plus 1, and we get x plus 1. Now we can subtract that from what is left over. We could keep repeating this process indefinitely. But remember how sometimes in long division, if a number is not perfectly divisible, we get a never-ending decimal. For that same reason, we take the remainder. The remainder is whatever we are left with when we reach the constant term at the bottom. And just like that, the quotient is whatever is on top plus the remainder. The remainder is always expressed as the remainder divided by the divisor. Make sure you understand why. Let's try another example. Here, 4x squared would perfectly divide 4x to the fourth, so we multiply that with the divisor. Now we subtract that from the dividend, and repeat the process again and again until we reach a constant on the top of the division bar. Be careful here when finding your final result. The remainder is not negative 3x plus 29 over x squared minus x plus 2. Now you've gotten your feet wet with long division, but there's another method to quickly find the quotient of polynomials. Synthetic division is essentially long division but abstracted in such a way that is faster. This is the divisor, this is the dividend, and this is the quotient. The middle row is the thing you subtract by. All the information in a synthetic division is contained in a long division, but we avoid writing out what is repeated. First, we write a rear out. Next, we write the divisor. In synthetic division, you only care about the constant term. We always assume that the divisor is in the form x plus some constant. So, take the constant. But it also has to be in its opposite sign. The reason we take the opposite sign is that in our long division, we always subtracted the numbers. In synthetic division, we are going to add them. Then we insert the coefficient of each term in the dividend. The first number you write is the coefficient of the largest exponent, which is 1. Then you write the coefficient of the second largest exponent. The coefficient for the term with x squared is 0. Then it's negative 6. Then 2. Finally, we evaluate the quotient. In long division, we would find what would divide x cubed. X squared would do that, so we just copy it down. But, just like the dividend, you only put the coefficient, which is 1. Now, we have to subtract x squared times x plus 3, which is x cubed plus 3x squared. But here's another shortcut we take. We already know that the x cubed terms will have to cancel out, right? I mean, that's the reason we know x squared is the first term of our quotient. We selected it because that is what will make the x cubed term cancel out. So, the x cubed term can be ignored at this point. We just have to write the 3x squared. The 3x squared is going to be subtracted, so we write a negative 3, which is the coefficient. The subtracted number will turn out to be negative 3x squared, right? But don't write it down yet. This is yet another shortcut, since we are assuming that the divisor is in the form x plus c. The coefficient of the subtracted number here is a part of the quotient. Why? Because dividing by x plus c, if you only pay attention to the x, it's just dividing by 1 times x. So a part of the quotient is just going to be negative 3x squared divided by x, which is negative 3x. Now we need to subtract negative 3x times x plus 3, which is negative 3x squared minus 9x. But again, we can ignore the negative 3x squared. That leads to negative 9x, but since we are subtracting negative 9x, we write a positive 9. The subtraction leads to 3x plus 2, but 3x over x is a 3, so a part of the quotient is 3. Then we subtract 3 times x plus 3, which is 3x plus 9. We ignore the 3x and write a negative 9. Subtracting these leads to a negative 7, which is our remainder. The quotient then translates to 1x squared minus 3x plus 3 minus 7 over x plus 3. The first term is not x cubed, it's x squared. If the quotient was x cubed, that wouldn't make sense, would it? The combinations of these shortcuts leads to the following sequence of steps. First, set the synthetic division up. The divisor is the opposite of the constant term. The dividend is each coefficient of each term in decreasing order of the degree. Second, copy this first term to the bottom. This works because, as we saw, we are just dividing by 1 times x plus some constant. Third, multiply this copied number by the number here. We do that because, since we know this to be the part of the quotient, now you have to subtract this times the divisor. That product is copied down here. 4. We just add these numbers. This is like long division, but with opposite signs. In long division, we subtracted the product of the quotient times the divisor. Here, we are adding the product of the quotient times the divisor with the opposite sign. That's all you need to know. Now, you just repeat steps 3 and 4 until you reach the end of the line. The quotient here is 8x cubed minus 6x squared minus x plus 2 plus negative 7 over x plus 1.